This is our project for our design class. We basically want to do a traffic flow optimization problem. So ideally the case is, we'll pull right in and we can show them our intersections. So we have two adjacent intersections. So the idea here is that we want to minimize the backlog that happens between the intersections. So the example here is that we have one high flow lane coming in from here. So this is like a main road. This is another high flow lane. And these are residential streets, so they're low flow lanes. The numbers we use for them is about 20 cars per minute for high flow and 5 cars per minute for low flow. That's actually exactly how much we do it. And we use a tick-based system to do it. So one tick, whenever I refer to ticks, it means like one calculation or like 1 second in simulation time. So the purpose of our idea is that we want to obviously reduce the backlog between the two streets and also make it at a reasonable cost so there's not a significant like overhead for implementing this technology, especially since we would more likely use this in more rural streets or like things that like are like and you wouldn't want to spend a lot of money there, like it's not like a downtown street. So some difficulties that we do want to mention before we start getting more into this is that as you can see, only half our board is lit up, and that's due to some difficulties we faced in timings and organization and things like that. And we have the proof of concept and we can show you that this would work just as well if we just wired it up. But if you pull down for a second, it's already become a mess when we just did half the wires. And also the wires, unfortunately, are not of very, very high quality. So sometimes we have disconnects even though there's not really anything we can tell that we're disconnecting from. So hopefully you can understand where we're coming from, but we do have proof of concept that all of it would work. And so the layout itself, like we said, we have a high flow lane, low flow lane, low flow lane, and then these are the middle lanes. We call these M1 and M2. So if you ever hear us saying later on in the code that H1 has something value, that means this street. Also, we have named our exits too. It would be, I believe it's E1, E2, and E3, and so on. So basically we can count the amount of cars that leave, but that'll be more for the part 2 of our presentation where we actually run the simulation all the way through. So the communication now, so we want to, as you can see, there's a lot of wires to just run for half of our board. So we wanted to break up the load by using 2 Arduinos instead, if you want to pull down here. So we actually use communication between the 2 Arduinos. So our main Arduino over here does all the calculations, like as in like the traffic flow calculations, does all the traffic lights and counts how many cars are in each intersection. And then the only thing it actually pushes to the other Arduino is the amount of cars that are waiting in the separate lanes over here. So like we said, it's hard to see like, oh, how does that work? Well, we can actually show proof of concept because we can see the amount of cars that are the numbers that are going to be pushed through. So in this case, we have 1, 2, 1, 1, 0, 1, 0, 1, 1, 0, and 0, 0, 0, 2, 2. Now if we pull here, this is actually the input. So this is not as clean because you're not actually supposed to see this, but you can see that here we have 0, 0, 2, 2. And whenever we have a number, like I'll just read it from here, 0, 0, 1, 0, 3, 3. And then we'll see it show up right there. Sorry, 1, 0, 3, 3. So it actually does show up, even though it's kind of a little bit hard to read because it keeps going by. But our communication and like number transfer is working. So it is a proof of concept and it would work. And in part 2, we'll actually show you the simulation and the results of the simulation, because this is more to show so you can understand how the traffic flow is flowing. But the actual results in the simulation we'll discuss more in part 2. Thank you. So this is part 2 of our presentation. Now here we want to actually show you guys the results, like the full simulation after it does 1,000 ticks. So so this is an older version of the code that we have here. The actual code itself isn't that important, but the point is that it's an older version of before we uploaded all the delays so that the displays can work and all the things like that. I'm just going to upload the code and open up the serial monitor. So it's going to quickly go through all the ticks. It probably could go faster, but I just put a limit so there's no like transmission errors, but for a different reason. But anyway, the ticks count up to 1,000. Now it's done up to 1,000 ticks. So now we have 1,000 ticks done. So at the end, it shows the results. Like for example, here we can see all the cars that are waiting at the intersections, at the different intersections when the 1,000 ticks are done. For example, at the high flow 1 lane, there's 2 cars waiting. The low flow 2 lane, there's 3 cars waiting. There's 3 cars waiting in middle 1 and 0 cars waiting in middle 2. But the more important stats for us are the exit stats. So it tells us, it breaks it down for us. It shows us how many cars left from each exit that we labeled. So in exit 1, 177 cars left, exit 3, 164 cars left, and 172 cars left from exit 5, and so on. We can see all of them. And then it adds them up by intersection. So 498 cars left through intersection 1, and 553 cars left from one of the exits in intersection 2. And so our goal was to like ideally the goal is here is that in 1,000 ticks or 1,000 calculations that represent like 1,000 seconds, and in simulation time we wanted roughly 1,000 cars to get through, and we had that. So at the end we were able to reach 1,051 cars to go through the intersection in 1,000 ticks, and I believe that means it's a success. We were able to hit our goal, and I think that's our whole simulation software. Thanks.